Okay, in this video, which is the final video in this series for stress transformation, I would like to discuss the analytical method for 3D stress transformation. So we have 3D stress, let's call it we call it sigma ij, equivalent to Sij as I used in the previous videos for designating stress. Now, when we have 3D, we are dealing with a matrix of 9 components: sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, and sigma 3, 1, sigma 3, 2, and sigma 3, 3. Now, having a coordinate system, always like what we have, let's designate a coordinate system here, Z, and also use symmetry. Because most of our, this method that I am going through doesn't need the requirement of the stress tensor being symmetric, but most of the time it is symmetric. So if you have symmetric, the calculation simplifies. Otherwise, the method applies and the procedure can be applied for calculation. So here we call it sigma x, and then maybe tau xy, tau xz. If it is symmetry, then this is equivalent to tau xy. Then it is sigma y, tau yz. Tau yz. And then symmetry again, and symmetry, and sigma z. Again, if you don't have symmetry, big deal, we can apply the same thing. So I will continue with these notations. So what's the objective here? Objective here is that we want to transform this stress tensor, which I discussed before. So if you transform it to a rotated coordinates, like x prime, y prime, z prime, you can calculate the components of the stress in the rotated coordinates as we discussed before. So this we know how to calculate the rotated component. Now here, but we would like to calculate the principal stresses. Let's call these principal stresses, say sigma 1, sigma 2, and sigma 3. We have 3 principal stresses because of 3-dimensionality of space that we are dealing with. Now maybe I zoom in a little bit to have more room and then continue. Okay, we have to go back to the principles, and then if you have a medium, let's say a medium, yes, my automatic shape is on, I don't want this. Let's draw the arbitrary shape here. This is a 3-dimensional shape. at any material point on this, in this domain, in this medium, I have a strain acting on that point, as shown here. Now, if I come and identify, maybe change color here a bit to be more clear. If I come here and apply a surface here, or choose a surface direction, then we draw these things again, sigma ij at this point, and then this is my plane. Now, there is a formula that says that the traction or the force on that plane would be sigma ij nj. This n is the normal to the surface, outward unit normal. So in other words, I identify this surface with a unit normal, Ni or Nj, doesn't matter. Therefore, as a result of that, I may get a traction. This traction is not necessarily in the direction of normal. Let's say traction Ti. So this is traction. Traction is the force on that surface. This is so-called Cauchy's formula, that if you have a stress acting on a point, or any point has a stress, considering this arbitrary point, and then you consider an arbitrary orientation of a plane, the traction of that plane is given by this formula that I'm writing here. So if you want to expand this, basically is T1, the first component, first being x. So let's 2, 3, and 1, 2, 3, and x, y, z are interchangeable here in this discussion. So T1 is sigma 1, 1 and 1 plus sigma 1, 2 and 2 plus sigma 1, 3 and 3. And similarly, T2 is sigma 2, 1, which is actually sigma 1 and 1 plus sigma 2, 2 and 2 plus sigma 2, 3 and 3. And finally, T3, the third component, is sigma 3, 1 and 1, sigma 3, 2 and 2, and sigma 3, 3 and 3. So these are the three components of this vector Ti. Simply calculated once you know the component of the stress. And I kind of skipped writing the prime for simplicity. So this stress could be the components of the rotated or any initial or any state that you desire to calculate the principal direction. But when you go back to the previous discussion, and if you go back to the Mohr circle, we get the, I designated S, which is sigma now. So you initial state, and then you get your rotated based on the Mohr circle. Similar here. Now, once you have that, then you come here and say, okay, two things here is happening. First of all, that we have to pay attention to it, and that is this plane is arbitrarily oriented by Ni. It could be any orientation, right? It could be any orientation. And depends on Ni. I will not crowd the picture here, but depends on any orientation. you will get an NI associated with that orientation, which is the outward unit normal. Okay, and then based on your second is based on your stress tensor and this orientation, you will get the traction. As I said, this traction is not necessarily normal to the plane. It could be at any orientation that your result will give you that components. Now, what we do here is that we come here and I draw it again kind of here to show you. Maybe I do it with the geometry shape here. Maybe sometimes this becomes sticky. Sorry about that. Okay, that's good enough. Don't want to waste time on this. So this is your plane. So right now I will have a traction on this surface. So I had to stop the recording because my computer stopped responding. But we are back. Okay, on this plane, which is shown here and kind of in two-dimensional here, I have a traction. Now what I do, I will come and get the component of this traction in the direction of the normal to the surface. And I get an N, shall we say, component. And later we will get the traction in the plane, which is basically the shear in this plane. So please be aware that if you choose a different plane, these components will change. And depending on the plane, you will get your traction. So this is my T as a vector, N and tau as a vector. We are interested in this N, which is the normal component to the desired selected plane. Why? Because we are interested in principal stresses. So I want to find an orientation such that this plane, when aligned with that orientation, this N becomes maximum and tau becomes 0. That was the definition that we had before, right? For principal stresses, if you recall, for example here, sigma 1 and sigma 2, these are principal stresses, and at that orientation, the shear is 0. We want to do exactly the same thing, but in 3D. So I want to find an orientation Ni such that my N becomes maximum. And in order to do that, there is a mathematical procedure to do that. And I refer you to a reference shortly if you are interested how to get to this result that I am going to write here, which uses the Lagrange multiplier method as well as the requirement of a unit normal, which is the component, the sum of the square of the component of Ni should be 1. and then after some optimization, you get an equation. So to have, let me summarize it here, to have n as the maximum, or shall we say principal stress, that procedure, mathematical procedure, will give us this equation. Sigma ij minus lambda, which is a coefficient, we call it Lagrange multiplier, delta ij, nj equal to 0. Required. This equation should be satisfied in order to have what I just explained here. And maybe I quickly repeat, I want to find the orientation of this plane such that my n becomes maximum or only stress at that direction. Basically, tau will vanish. And you see that easily if I rotate this plane such that my n and traction becomes, aligned, and therefore there is no shear component. So this relationship will give us that. You remember this is canonical delta. Delta. And to refresh you, this is 1 if I equal to j, and is 0 if I is not equal to j. Sigma ij is our stress tensor, lambda is a parameter here, and n is our normal to our plane. So this is very good. So if you write it in matrix format, this will become, say, sigma 1 1 minus lambda, and then sigma, say, 1 3, sigma 2 2 minus lambda, and the rest of them, and sigma 3 3 minus lambda. I don't write the rest of the elements here, but basically this will be the diagonal, because only diagonal, at diagonal delta ij is non-zero, but for the rest of the elements it is 0. And then here you get n1, n2, n3 equal to 0. So we would like to solve this system of equation. From linear algebra, you realize that the arbitrary solution for n is, because the objective is n, is 0, because the right hand side is 0. So this is primarily solution, but not acceptable. We cannot have a 0 orientation for a plane. We should have some number. And the trick is that we come here and let the determinant be 0, be equal to 0. So in other words, sigma 1 1 minus lambda, sigma 2 2 minus lambda, sigma 3 3, if I go 3, and then dot 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 dot, determinant, not the matrix, becomes 0. If this happens, then I will get a non-arbitrary, shall we say, equation, and out of here, out of this, we get a cubic equation for lambda. That cubic equation has a special place in this type of calculation. I write it down here, and this is lambda 3 plus I1, and I explain what is I1, lambda 2 plus I2 lambda, and sorry, this should be minus, and then minus I3 equal to 0. This is called characteristic equation. For symmetric, most of the cases that we have in practice in engineering, we have three real roots. Not always cubic equation have real roots, but here we call it lambda 1, lambda 2, and lambda 3. Can call it also sigma 1, sigma 2, sigma 3, and these are eigenvalues, so-called, of your matrix, or the one that we are interested, principal stresses. So let's wrap up what we have said here. We start with a stress tensor. We identify a plane by outward unit normal. We find the traction, and using Lagrange multiplier method, we come up with an equation that gives us the maximum value for n, or a function which involves n, and that operation will give us this equation, which is sigma ij minus lambda is a parameter, delta ij nj. So this should be satisfied. Now, once you look at this, you realize that it has an immediate solution. If you put n equal to 0, all of the components of n, the outward unit normal, this is satisfied. But we are not interested in that. So in order to get a non-zero solution, we come here, and this is determinant of this system. Determinant should be 0, and that determinant gives you a cubic equation. The roots of that cubic equation is your principal stresses. That is the summary of this method. Now, I have to identify I1. These are called invariants. I1, I2, I3. Invariance simply means that if you rotate your coordinate system and calculate your components of your stress in the rotated coordinate system, obviously the component will be different, but these three will remain the same. This is also true for your principal stresses, eigenvalues. That's why these have special names. They remain the same due to rotation of your coordinates. So these invariants, the first one is your trace, which is sigma I. The second one is the sum of diagonal minors, if you like. If I write it here, this is also equal to lambda 1 plus lambda 2 plus lambda 3, but before you solve it, you don't have it. So we should write it in terms of the sigma, and that is the diagonal minor. So this is sum of diagonal minors. Diagonal minors, meaning that you come here and for your stress, you eliminate the row and column corresponding to each diagonal element. For example, here, this row, and calculate the determinant of remaining. And next one, you come here, sigma 2, 2, you eliminate column 2, row 2, and calculate the determinant, and similarly for the third element. So these are diagonal minors if you want it in, and the third one is actually the determinant of sigma ij. Okay, so I don't write the longer expression. You can calculate it, and then that's it basically. So these are how to calculate for any three-dimensional. It is pretty solid, and you don't need to make any assumption in terms of symmetry or not. But if you have symmetry, obviously things will be simplified a bit, and then you can go after that. Following this, you can actually calculate the eigenvectors. Eigenvectors or principal directions. And how do you do that? I will not go through the details here, it's pretty lengthy, but for each lambda, which is lambda 1, lambda 2, lambda 3, these are our principal stresses, solve the system. Meaning that you come here and then you say, okay, for, let's say for lambda 1, I have, this is the main equation that we are focusing on, just to, this is the equation that I'm talking about, this system. So for lambda 1, I will have sigma 1, 1 minus lambda 1, sigma 1, 2, sigma 1, 3, sigma 1, 2, let's assume symmetry, sigma 2, 2 minus lambda, sigma 2, 3, sigma 1, 3, sigma 2, 3, and sigma 3, 3 minus lambda. So these are my coefficient matrix, and then I have an associated n, let's call it n1, n2, n3, and I put a lambda 1 here, not to crowd the symbols, but this is basically the principal vector or direction associated with lambda 1 or sigma 1, if you like. So for any principal stress, we need a corresponding orientation. This is what we discuss in the example, numerical example. You see, for this one, I have an orientation, which we showed it here, and similarly for shear. So this is what it is in 3D. So the solution to this equation actually equal to 0, with the requirement that n1 lambda 1 square plus n2 lambda 2 square plus n3 lambda 1. It shouldn't be lambda 2. It should be 1 because I am only considering for the first one. Okay, sorry for that. This is lambda 1. Lambda 1 square should be 1. Sometimes this is funny, but okay, let me write it here, equal to 1. So this is your condition. So if you solve this system, the solution for the n will be your principal direction. And then you do similarly for lambda 2 and lambda 3. You get, n1 lambda 2 and 2 lambda 2 and 3 lambda 2 and 1 lambda 3 and 2 lambda 3 and 3 lambda 3. Okay, so this is for this one and this is for this one. So this is how to do it fully, completely, without any assumption needed to impose on your initial stress in terms of symmetry or no, but most of the time we have symmetry and we benefit from that. Maybe I kind of a little bit zoom in. And then therefore we can beautifully do this. Yes, it is more lengthy, but it is more complete. Maybe you want to use some software tools like, I don't know, I don't name anything here, but there are several symbolic software that you can use, or maybe actually you could code it yourself to do this, and then you have a complete tool for principal direction, and of course this will extend to shear and so on. So I would like to end this with give you a reference for if you want to dig into more details or see some examples, and that is one of my publications, Tensor Analysis for Engineers. Third edition. By myself, and the publisher is MLI, and the year of publication is 2023. This third edition is the latest, most complete one. So if you like, you can get a hold of this reference. That could also help you with supporting reference for all of the discussions that we went through here. Thank you. Hope this series help you master the stress transformation from 2D to 3D in general, as well as the Mohr circle that I found sometimes is not very clear, or people are not clear with how to construct Mohr circle in confidence. Thank you.